Okay, let's see if we got anything here. Okay, let's see if we got anything here. All right. So, first of all, let's head back over. I am sorry I'm out today, but thought it might be prudent to be careful. Oh, let me get this cut off. So now I know the stream is working well. Okay, now another stream is working, so, and I tell you what, let me launch it on the other computer over here so I can watch it from afar without the volume to make sure everything is operating correctly. Stream is working, so let me cut the volume off over here. Okay, so our volume's off over here. All right. Okay, so I opened up several of the other weeks throughout here. This is week 5. So if I head down through here to this is week 5, of course, that I was just at. Of course, I opened 6, 7, and 8, and 9 together. This is generally the period that's the reason I put that together is generally that's about the period for the midterm. Actually, it probably should be this week, but it ended up being the 8th, 9th. So I opened all those up. If you go in here to the 5th, you'll see some of, I would definitely watch some of these videos and then go down here and look at that homework, which is 5. And you'll see it. So what I did is I downloaded it, copied it to my local machine here, and brought it back up in here. Because the last lecture was on this topic. So I'm going to just go through how you would do, there are only 3 of these. There's this one. And actually, if you look real close, you've got that one. It's essentially the same picture with slightly different questions on it. So technically, I guess there are 2 problems here. So if you look at it, you have to realize that your goal to start with is to find, is to find R and dr dt, and I'll go ahead and write it this way, which is just r dot, and second derivative of r with respect to time, which is just r double dot. Then when you find it, you might be able to do this independently, but this will usually be given somehow. In other words, determine the velocity. Well, this one's a little bit different when r is equal to this. We'll go back through this in a second. Hang on. Then you find this. Oops. The dot off there. And then the second time derivative with respect, or second derivative of the theta with respect to time, or theta double dot. Excuse me. Then you use these in those equations. To remind ourselves, let's look back. And there's one page in there that does a pretty good job of putting them all together. Okay, it's obvious that, not obvious. It's either this problem or that one. I don't know. We're going to look at the problem itself, but that's where I got it from. You run back to here. This is the one that to me encompasses everything. And that's this equation. They didn't box it or make it blue or anything like that. I would have done that one. It's okay. I'm just going to copy that one for reference. I'm going to, oh, wait a minute. I can't put that there. But I can work the problem over here. So that's what I'm going to do. So actually, this might be a better place to work it anyway. So what I'll do is have that for reference. I'll go back over here. Go, and now I've got to find the problem, which I think that's it. Yeah. Okay, so now that I'm doing it off of this, and I should have pre-prepared this, but grab this, put it over here. Put it over here. And I'm going to grab the text. Put it over here as well. I guess I'll put it below it. So now we're in this application. The slotted link is pinned at O. That's the origin that he's using there. As a result of constant angular velocity of 3, it drives the peg, this little P right here, for a short distance along the spiral guide. It looks like that, where that's in radians. Determine the velocity and acceleration of the particle in the instant it leaves the slot. Oh, okay. It leaves this part. At r is equal to that. Okay, so this is kind of a backhanded way of doing things. Let's see. When r is equal to a half, then I did not start octave here. Okay. 0.5, roughly 0.4. I am a little bit interested in something, and that is, just as a side issue, I want to know, he's not asking this, but I'm going to say, how many degrees is that? So 1.25 radians, and there's 180. I'm just going to use the degree symbol here and do like that. Degrees every radian. what that is. But I put the wrong button here. Push that times 180, and there should be 180 degrees under a pi. So I didn't complete that. And I better check. Yeah. So it's 180 degrees over pi radians. So 71.62. In other words, I forgot something right here. I didn't put the number. If I put 360, that would be 2 pi, but this is just pi radians. And so he's telling me, you know, that's about 71 degrees roughly. That's just something I wanted to know. And the reason I wanted to know that is because I wanted to get a feel for the drawing and whether he's got this. In other words, this thing could go past that if it wasn't going fast enough, but he's got it drawn to where the tip of this looks like it could leave at about right there, which that's about right, I guess. So, facts. Theta is equal to, okay, you've got a choice. In this particular choice, I'm going to say our 1.25 radians, or roughly 71 degrees. Theta dot is equal to a constant angular velocity, which just means that this is the case. Now you go over here and you use this equation. So you need to find out R, which it's just straightforward. 0.4 theta. R dot. And why do you need each of these? Okay, so if you look at this equation, kind of ignoring these terms, because this is cylindrical with this. In other words, cylindrical coordinates are basically something like this, where this is maybe, I know this looks strange, but the theta is measured here, and there's a z component. But if you don't have a z component, then you have 2 dimensions there. And that's what we're operating in. It's just 2 dimensions. And so, let me see if I can figure out how to cut this notification off so it quits dinging. Oh, the mail. Okay, let me get rid of that. Okay, that may make it so it no longer dings in the middle of what we're trying to do. Okay, so now, what do you have here? Well, obviously I have R. I have R dot. Now I do have the appearance of R double dot once. So let's look at it like this. What do you need to know here? To find your R, you need to know R. To find your velocity, you need to know R dot. You need to know R. You know theta dot. All right, because there's R dot, there's R, there's theta dot. What do you need to know? If you need to know acceleration. You know R, you do R dot and R double dot. So just like this, you know R, R dot, R double dot. And what do you need to know? Theta dot, theta double dot. Notice in here, there's no real specific implied location for this. However, it's there because you're going to find, if you're looking for the acceleration or say the velocity, you're going to be basically looking for at let's say 30 degrees. So the 30 degrees is what you're going to end up with. You're going to end up with r dot. I'm just copying this down. R dot at and then UR, and technically this should say plus these two terms, R theta dot U theta at theta is equal to 30, theta is equal to 30, and theta is equal to 30. So this is what you got. You've got this embedded in each one of these. So that's why it's not explicitly there, but it is in there. So let's go back to our problem. If you want to know r dot, oops, looks funny, dt is equal to dr d theta dt. This is pretty well known. And so what you get, theta dot times derivative of 0.4, and I'm just copying this and putting it right in there. And it's basically going right here. I took the theta dot, put it right here. Well, okay, so I can bring that 0.4 out, and I just get 0.4 times theta dot. Well, did I circle around? Yeah, because this was and could be specifically specified as theta is a function of time. So I could have just dotted it and I would have got the same result. But I wanted to go through this exercise to get us prepared for any future possible steps that might even occur soon here. So here we're looking at this. And in this particular case, I don't think there's any reason to go through this, because now I take the time derivative of that and I get that. Now I don't think, oh, he did say he wanted to find the acceleration too. Now let me see, I'm intrigued by this now. Oh, wait, this is, let me go back over to here in the problem statement. And so there's your answers right there. So heading back over here, hang on. So let's list them again. Or actually, I don't even need to do that. We listed these straight up. We listed these right now as variables. This is kind of confusing right now. So what we're going to do is rewrite it in a little less confusing way. Now, what we're doing is we're going to actually find this r at theta is equal to 1.25, and that's going to be equal to 0.4 and 1.25, and wrong one. Let me go back here. 0.4 times 1.25 should bring us back to the half. that was initially stated right back here. Now we should be looking for r dot at theta is equal to 1.25, and this is in radians. Well, as it turns out, you would simply go 0.4 theta dot at theta is equal to 1.25, and guess what? That was given to you. So that's nothing more than 0.4 times, I believe it was 3, or I believe that's 1.2. Now I can do the r double dot at theta is equal to 1.25. And when I get there is 0.4 theta double dot at theta 1.25. However, he told us it was a constant angular velocity, meaning that if this is constant, it doesn't vary much. So it doesn't vary at all. So therefore, you could look at this and say that's 0. Well, that's 0 all the time, and this just becomes 0 here. Now let's look at what we have. And in my equations, I'm going to write them over here. All I need is theta dot equal to 3, theta double dot equal to 0, r equals to 0.5, r dot equal to 1.2. So I'll put these two up from here, and I'm picking these 3 up from right through this. And I'll say r double dot equals 0. Now, I'm going to go in here. Let me zoom in here. And let me get rid of this mess all over the place so I can just look at the equation and say, let's start with the V. So the velocity, it says, is equal to r dot ur plus r theta dot u theta. Well, that's just 1.2 times ur plus r, which is 0.5, that's this, times 3, which is this, and that's u theta. So we get 1.2 ur plus, looks like 1.5 u theta. I don't remember. Okay, he gave just, I didn't want to go back there. Let's go back here. He gave us the, if I just hover there. Oh, yeah. Okay, so he did give us both components. If you look, there's a VR and there's your V theta. So all you do now is you insert those values in here, and you can, it's nothing more than determining those values and inserting them into those equations. So go ahead and do that on these last two, but what I'm going to do is I'm going to divert a little bit. And what I'm going to divert to is I'm going to say, what is the physical meaning here? And I'm going to focus in on this and say, and assume the drawing looks reasonable. I'm going to copy it, and I'm going to put it over here, and then we're going to do some extra work on it. And here's the extra work we're going to do. Okay, so we figured out that it was roughly 71 degrees, or let's see, let's go back to my calculator, 71.62. So at approximately 71.62 degrees, okay, so hey, this has no oh, it took it out. This has only integer values, so at 71.62 degrees, we reach up here a distance of, and that distance should be 0.5. At that particular point, and let me draw my ruler back up. This time, okay, actually, come on, there you go. Yeah, actually, it should sit right there. Oh, there we go. What I was trying to do is line up these two toggles there to show that it's 90 degrees, at least to me. And I'll have a vector that goes off here. Okay. Yeah. Okay. Fingers as far away from each other as possible. Yeah, move one finger, not the other. Okay. So, here's what you see. You see the UR vector and the theta vector, where this is theta right here. This is pretty convenient. So this is about 1.2. Let's assume this is about 1. And what I'll do, I'll say it's about 1, and that's 1.2, so it goes out to about right here. So this vector is 1.2 times UR, and then what you get here is a slightly larger value, about 1.5 U theta. Now, okay, let's see. It was 19. Yep. I didn't do a great job of it, but I did something. Now let's see. Could I even imagine, and I can make a halfway hearted attempt here at it, that this is the actual final velocity vector. Now if you look at it and you drew this out on MATLAB, you would find that it would be tangent to whatever this path is right here. But my next case in point is, what is its value with respect to I and with respect to J? So you come back to the base equations, which is basically UR, this little base vector right here, is, and I've done this in previous lectures, but it's cosine theta I sine of theta j. In other words, if you had, I'll do this real quick, not very accurate, but you take your UR, you basically have a theta, And this is u theta, the magnitude, magnitude of ur, which is 1, times cosine of theta. And this length is 1 times sine of theta. So in fact, if you look back at some of the stuff I've talked about before, now it turns out u theta it's basically this. So again, u theta sits here and points back this way. Here's I, here's J. This right here is theta. So actually, I should shrink that down a little bit, or no, I'll grow it. This is theta. So here's the y component. Here's the x component. I guess I could draw it like right here, which is the same distance as here to here. Nothing more than. The difference is it goes in the minus I direction. So you have a minus there, and you have a plus there. So now that you have those broken down, you can simply just say, well, theta is 1.25, and you have to make sure you're using radians on your calculator. So let's break it down that way first. Cosine of 1.25 radians plus sine 1.25 radians. And theta is minus sine 1.25 radians plus cosine 1.25 radians. And so, let's see if I can, yes. Oh, wait, that's the wrong button. Okay. Okay, hang on. Sine 1.25, 948. Okay, so let's just do this. Cosine of 1.25. Let's see if I can copy this down reasonably well. Let's do the sines first. Turn the keyboard so I can pick them off. 0.948. 98. $31532. And we're going to see if this makes sense to us. Now, I could even go further with this, but I think I will, just out of curiosity. So now you take 1.25 times this. So if I want to know the velocity in Cartesian, I would sit there and take 0.25 times UR plus 1.5 times U theta. And I just copied this over, but I wrote them vertically. The reason I wrote them vertically is because I'm going to erase this and replace it with 0.31532 I plus 0.94898 J plus, I'll erase this one, minus 0.94898 I plus 0.31532 J. Now, guess what? All I have is I and J here, but I've got to go through and figure these out. So, and let me do that real quick. So the way I'm going to do this, let's see, there might be a better way to do this. I'll just do it the long way right now. I'll do it like this. U, R, and I'll list them in their component value. Okay, so here's what I mean. Take UR is equal to 0.3153, and then I'm going to put a print, I'm sorry, I should have, I'm looking at these in component form, 0.94898, and I got it. So that's the UR. The X component's the first one, the Y component's the second one, U theta, I'm just going to call it U 0, and it is minus 0.94898, comma, 0.3153. Uh-oh, I messed up the other one. 3153, and I could have put a 2. Yeah, it's probably close enough. And now what I want to do is just multiply 1.25 times UR plus 1.5 times U theta, and end up with that. Now let's look at 1.02, 93 minus I plus 1.6592J. And does it look similar? Well, yeah, it's going up and it's coming back to the left. So it looks okay. So this will give you an idea of how to convert. Physically what you're doing, you should really look and think about what you're doing, not just try to get the answer, but think about it in a drawing sort of sense there, and how you can make your way through it. I was promising I was going to do something else, but I'm not necessarily running out of time, but I'm pretty close to it. Since I'm here, it may be instructive to try something interesting here. Since I'm on this topic, I'm going to list things in an interesting way. And give me a minute here. So if you think about it, if I listed UR and U theta in a coordinate system like this, give me a second. I'm looking over here at this, putting it into matrix form over there. So now, it turns out this is often called the transformation. Matrix. So if we, and we probably could find that if we, and I'm sort of diverting because let's see if I can find this. There is, let's see. Let's see if I can find this. This might be, I know there's a lot of different things out there. If you're taking linear algebra, you'll see this. But in a physical sense, you're seeing it just like this. You can kind of look at it like this X and Y, and X and Y here, and X and Y prime. It depends on how your like in here he's saying, how is theta measured? Is it clockwise or counterclockwise? And that's kind of what changes the sign on the sign, and that's it. You notice everything else looks the same. So this is similar to that, and actually is the exact same thing. There are other forms of transformation, but in a general form, a transformation moves you from one set of variables to another. And in this, it's moving you from the polar coordinates back to Cartesian. And so that's what this is right here. So just as a point of reference, if you do decide to go at some point in your future to a graduate program or something. Okay, let's look and see if we can start chipping away at this second one. Let's first try to identify what it is we're going to have to do, and then we'll come back to things. You may have to come back to this next time, but let's just start it off. The rod OA rotates clockwise. He shows it right here. At 6 radians, the 2-pin sliders located at B move freely on this rod and on the curved rod. And shapes form of a leprechaun or whatever. I'm just making that up, but that's not what that word is. And there's your equation. Determine the speed of the slider blocks when it's 150 degrees. Now, it's kind of interesting. He's measuring theta from here. So the first thing is, let's identify constant angular velocity. Theta dot equal to 6, but guess what? It's actually a minus 6. Why? Because this is the positive direction and this is moving the other way. So it's like a minus 6. It's constant, so it's 0. So we have those two figured out. You have also 50 degrees. Now you're down in here doing this. Your next goal is to take R and then find R dot and then find R double dot. So that's our goal right here. 200. We already know what that is, so let's just go straight after R dot. R dot is equal to, should have done it the other way, but we don't have R listed as a function of time. It's listed as a function of theta. That gives me theta dot, which is this term, and what I'll do is 200 2 minus cosine theta, or if you want to list it, maybe we'll go down here, take the 200 out, put the 200 out here, and take the 200 out, and I'm going to go, I know this is crazy, but I'm going to include that term minus okay. You know that this is a number, has no variation in 2, so you get nothing there. So derivative of cosine minus the sine So that takes care of that. So you get 200 theta sine theta and nothing else really. Now, your next goal, take our double knot. Get rid of theta, sine of theta, or let's sort of break this down. First it'll be this. Oops, sorry. Plus now this part's pretty easy. That's just theta dot. This part is really undoable, but it's not undoable if you consider this. This is doable. So I think what I'll do is just leave it at that for the moment and maybe pick this up. Again, I think, oh, here's the velocity. I guess the next one was maybe the acceleration. Yeah. So it's looking for the acceleration on the next one. It doesn't matter for both of them. You need to come up with this set. And so I know it's a minute or so early, but I'm going to draw it to a close. And, oh, word of the day. Never did the word of the day. This is dynamics. Tree. There you go. There's your word of the day. That'll give me an email back. Okay, so I'm going to go ahead and conclude this and drop ourselves out. And we'll go from here. I'm sorry for waiting till the word of the day at the very end, but